Okay, chapter 4 of the power protection, covering the elements of power system, the major element of the power system modeling first, and then talking about the load flow, and finally finalized by the worst of fault type, which is three phase bolted one. And you are going to learn how to model, how to do the power flow, and for power unit also is covered by this chapter. So the first component in the power system, one of the major, is the generator. When we're talking about the generator, we're talking about the source of energy. So the modeling of that one is a real challenge in power system. But because this unit is offered for the second year, I make it the simplified one and avoid any detailed one. So for you to know, in the generator we have two parts, which is rotational part. We call it the rotor one, and the stator, which produce or connected to the grid. Of course, the stator in the case of our generator model, synchronous one, is connected to the grid. Uh, by that one, you can find out. Okay, you can find out the armature reaction. What is the armature reaction? When the loading increase on the stator of the stator of synchronous generator, based on the Lenz's law, there is a negative effect which avoid to generating more power. This one is seen by the armature reaction. So the armature reaction is there, the negative effect of loading, and then the reactance of that one, because the of course the stator and the rotor both are rounded and the coil is there. So we will see uh, effective of reactance, which we call it XA armature. XA, the A is coming as armature, which is connected in series with the EMF. The EMF also considered as a source of energy. So this is you can call it positive, negative, which is because it's alternative, so time to time is change. Okay, and this is EMF, sorry, MF. Okay, and then simply we call this one as a voltage. So this is the voltage source, and then we will have a XA here as an armature reaction. And then after that one, because of coil, our coil, of course, the same as transformer, are not the ideal one. So we have another one, which we call it XL, which is the leakage reactance. So leakage reactance is coming in the way of the leakage flux going out from the core of the generator. So these two simply modeled by another reactance on behalf of XAXL, we should have XD and XQ. Okay. Later in the power system, if you join for the master and PhD studies, you will familiar. We have some transformation of ABC. You know, ABC is a three phase, correct? We transform it to DQ0. Okay, so ABC can be converted to DQ0 based on the matrix, three phase matrix. Okay, so I'm not talking about that one here anymore, about this one. Just to know, this is the direct reactance, which we usually refer to this one. Any X you see in the notebooks, in the books, or any catalogs is mostly referred to this one. Otherwise, it's very detailed one. And XQ is very a small one, so we usually avoid to talking about this one. Okay, so make it a simplified model. We have a source of energy. We call it V. This is V, and then we have XD by here. That's all. Okay. This is the modeling of the generator. So the generator. during the fault, considering different condition. Okay, um, I should talk about different type of generator. One generator is synchronous generator, which mostly you can find it in the power plants and means the hydropower and any means a coal one. In my view, all the big one, all the big power plants using the synchronous machine or synchronous generator. But in the small, for the small generation of energy, means source of energy, the same as wind, we usually use the induction induction generator, which is asynchronous one. So the reaction of these two generators during fault is totally different. We should divide the faulty condition to three major parts. The first part is consider fault inception, which is up to two cycle. Okay, this is very important. This one is very important and covered by this one. Okay, so when the fault started at this point, okay, is mostly considered by this point. Okay, if you want very professional one, it's at this point started and reached to this. Okay, the capping is coming by this curve at the top, so we call it subtransient. This one is two cycle. Okay, this one considered as a two cycles. And then we have a transient period, which is just after two cycle up to 25. So it is two cycle by here, here is 25. And then after this one is a steady state period. So the steady state period is the time that the you can see, okay, you can see in the subtransient we have a very high DC effect. You can see this is jump up because of the DC effect. If you can remember in the circuit and electronic, you usually model a circuit using L and R, and then you have two response, which was transient response, steady state response. Can you remember that one? So during the fault, the power system analyzed based on the same condition. So one is the steady state response, which coming by this part, and the other one is a transient and subtransient, which is related to the switching and the DC effect. So the switching is the meaning of switching is fault. The switching meaning for us here is the fault. Okay. Another important things I have to mention is, what's the meaning of two cycle? The frequency of power system in Malaysia is 50 hertz, correct? Okay, 50 hertz. Then the period of a sine waveform, a fully sine waveform from 0 to end, which is 2 pi, it's 1 over frequency, which is 20 millisecond. Okay, so this is one cycle. This is one cycle. 20 millisecond is cycle. Okay, one cycle. So when I talking about two cycle, I talking about 40 millisecond. So this is 40 millisecond. Okay, up to this point, which is 40, from 0 to 40 millisecond. Then 25 millisecond, which is this point, and coming from this word 25 transient, it's 25 times 20, which is 50, sorry, 500 millisecond. 500 millisecond meaning zero point 0.5 second, correct? So up to here is a half of a second up to this point. So I think you can understand how small is the timing when we're talking about the fault in power system. We must find and we must somehow quench it. Okay, again, I will return back to this name subtransient, transient, and steady state because of operation of the generators. So different generator on different timing, uh, and during fault produce different condition. Again, return back to the generator model. Okay, during the steady state, during the steady state, XL and XA, can you remember XL? XL was a leakage, XA was armature reaction. Only there. So you can see the values here. It's XD, okay? Then during the transient one, okay, XD convert to XD prime. Why? Because during the transient time, the field effect also is there. You can see field winding. What is the field winding? The field winding is the winding of the armature trying to induce voltage inside the stator. Okay, so that one also for a short while is in and affect the transient. So since XA and XF are in parallel, the value of this value is smaller than this one. Agree? And then XD becomes smaller. And finally, during the time of subtransient, not only XA and XF, but also the damper windings, okay? Damper windings also affect. So these three are connected in parallel, and the value of XA, the final XA, means the uh, equivalent of this one is smaller than all of them. Then you can see XD is the smallest one, and XD prime, XD double prime, and XD is the biggest. Okay, so this value return different condition. Another way of representation is calculating XD double prime, which is XL plus XA inverse, XF inverse plus XW inverse, all inverse. So you can, I think you can understand how the model it is. And for the normal condition steady state, this one is representing. So if we have different XD, which is XD prime and XD double prime, what is the effect on the current? Okay, you can see during, because XD double prime is the smallest one, correct? This is the smallest value. So since the voltage considered constant during all this period, the E or the V, whatever you like to call it, okay, is constant, and it is the voltage exactly before the fall of that point. Okay, you must divide this value by this XD double prime or this one, and then you can see the current during the subtransient is the highest compared with the transient one. This is the cap of the current. This is the cap of the current during the transient. So based on this, we can understand what is the meaning of current DC maximum. The current DC maximum is a square 2 of the voltage. This is the voltage of generator point before fault. This is the voltage before fault. I again insist. This is the voltage before fault given to you, okay? Over XD double prime. So this is IDC, the current DC maximum. And then IAC maximum is the voltage before fault over the XD double prime. And finally, if I ask you what is the RMS current maximum, is IDC power of 2 plus ACDC, then under square or by the power of 0.5. So it is square 3 of ID double prime. So this is ID double prime. This is IDC, which is times by square 2. This is IRMS, which is times by square 3. Then another important I have to mention, it's here. Okay, later I will describe that one. So I explained this one and this one. Okay, the next one I have to talk is the transmission line modeling. We have three different. modeling of transmission line. For the short transmission line, which are less than 80 kilometer, okay, we call it short transmission line, and the model is only one R and L. That's all, finish, okay? If it's between 80 kilometer to 250, these are not the constant value. Sometimes it is 100, but you means the book is still using the short transmission line model. So we consider it as a 80 as a somehow rough value for that one. So 80 to 250, we call it medium voltage or medium transmission line, and the model is coming out as a pi or T model. So you can see this is pi, okay? This is ground, this is pi model, this is Z, as the same as here, the Z, but here is Y, which is the capacitive effect over 2, half for the sending end, we call here sending end, and here is called receiving end, okay, receiving end. Again, y over 2 we have. The medium transmission line in another way can be modeled as a T, which we make the Z half, another Z. So this is our Z, this Z become half, so Z over 2 by here, Z over 2 by here, but on behalf the Y connected at the mid and fully Y is modeled by here. Both model the same is sending end, here is receiving end. Both model acceptable, but mostly they use the pi model. So this is pi model. Okay, you can see we using the pi model in this. And we have the line transmission line, which using the derivation and the equations to calculate the values. They usually use the matrices called ABCD matrix, and this value coming out using the equations, sine hyper, cosine hyper. Yep. Then you have to calculate. I think you will learn this one in the power system analysis, year 3. Then, okay, what is the Z impedance? The impedance in the power system coming in the way. Okay, the R is the conductor resistance. You know, for the 1 meter of any conductive material, we have a special resistance, whatever it is small. When we're talking about 80 kilometer or 100 kilometer, you can see the value become a big one. So the R become a big one. Then what is X? We have three phase. So the X is coming in this way. This is phase A, phase B, phase C. If you can remember, based on the Faraday law, and we have the effect, okay, the current of IA here. So IA based on the right hand affecting B and affecting C. In the same way, B affecting A and C and the C in the same way. So the reactance can be considered as that idea. And then what is the G? G is conductance between the high voltage transmission line, which here the voltage is a high voltage, and the ground. So there is a small leakage of the current between the high voltage and ground, which air is in between, correct? And then the capacitive effect. You know, again, here is a high voltage positive and ground is zero negative, okay? In between, we have air. It look like a capacitor, isn't? So the B is coming on that way. And again, don't forget here, the Z, the impedance, and Y, admittance, are totally different. The Y, here the Y is not equal 1 over Z, okay? The Z is related to the series component and the Y related to the parallel component of the power system. Then finally in the Y bus matrix, which covering both Z and Y, means the small z, this is a small z, this is small y, okay? Later I will discuss. We covering both side of this. Then, okay, the pi model I talk, so this one, sending end or receiving end is usually shown by a line in the vertical, which we call it the bus. The bus is the location. Usually, the bus is for me are substations, okay? But in some cases can be a bit different. But mostly for you to know is substation. So substation we have transformer is a location that we have many connections coming, going out. So substation usually considered as a bus place. And then don't forget here in this in our simulation and in our studies, Z and Y are mostly related to the voltage level. So they can be changed by the voltage level. And don't forget for the modeling of the load, okay, I think the next is load. I don't know why it's jumped up. The load model is the next one. We have three type of load. One is the constant power, which P plus JQ is the constant one. Most of the load we have are coming in this way. The other one is the constant impedance, the same as the heater. Water heater is coming in the impedance form. And constant current, which are the same as the LED or the arc welding or constant current. Then don't forget for the constant power loads, P equal VI cos theta. Okay, this is the formula for this one. So since we know the voltage and P, we can calculate the current, or on the other way. The motors and generator also coming on that way. Okay, they are constant power. Now we have two different type of motors, which is synchronous motor and induction motor or asynchronous one. During the faulty condition, the operation of this motor change. First, focus on the steady state, okay? In the steady state, after fault, after 25 cycle, okay? Both motors operate operate in a motor mode. But if it's subtransient, okay, you can see both operate as a generator. So be careful about this one during the exam or during the simulation or any of those. If I give you a synchronous or asynchronous motor, okay, during the fault, you must consider the synchronous motor as a generator for subtransient period, which is 40 millisecond for 50 hertz frequency. If it's 60 hertz, this one is uh, equal 60 inverse times 2 times E3 is 33.3 millisecond. So you must be careful about the frequency rate and also the cycle, how many cycles I tie. Finally, during the transient one, only synchronous motor considered as a generator. So keep this what we call it table in your mind because during the exam we also using this. The transformer model is fully explained in electrical machine. So R1 plus JX1 related to primary side or first winding, whatever can be high voltage or low voltage. R1 is related to the conductor resistance. X1 is a leakage resistance, with jumping out from the core. RC is the core resistance, which coming out from the eddy current and hysteresis. And also the XM fully coming out from the hysteresis. The next one is R2 and X2, which can be explained the same as R1, X1, but for the second winding. So this is the accurate model of the transformer. We never use such a model in our studies of power system because it's quite tough. So we're using the approximate model. The approximate model For the approximate model, if you can remember, we just move the parallel branch to the one side of the model, equivalent model, and then we have z equal, which of course it's r1 plus the a, which is effect of a, it was n1 over n2, n1 over n2, a2 over times r2, and for the x also in the same way, so jx 1 plus a x2, don't forget here you need power, and here is a plus. So this is the model, approximate model. Again, we don't use this approximate model. You know why? Because of this parallel branch make the studies quite complicated. So finally, and these values are always constant, and we can ignore it. The big value, this leakage is very small. The final value is, the final model we use is this one, only the series one. Even the R mostly is very small one, so we ignore the R also. The only one we use is X. So the transformer model is another studies which is only X. This is transformer model. After this one, we have to jump to per unit value. So per unit value, mm, I will upload another video related to transformer connection in Y, delta, and then grounding of the transformer, which are the important one. Also the grounding of the generator, and what is the effect of the zero sequence in the transmission line. So next is per unit system. Okay, what is the per unit system? Per unit system is a system in the is the unit per unit in the power system we usually use to avoid having a big numbers. Sometimes they ask you what is the voltage here in this line. They call it 750 kilovolt. What is the power? Means apparent power here is 40 megawatt. So you can see mega, kilo, such a big numbers, a real headache when we using the calculation. So on behalf of that one, we using a system, whatever it is three phase or single phase, we can use both in both systems, and make all the numbers in the range. So the standard range for us is 1 per unit, okay? But the numbers can be bigger and bigger than 1 per unit or smaller than 1 per unit. Okay, for the per unit system, we should know in power system we have four major quantities, which is S, and then V, and then I, and Z. So if you know two of these, the other two can be predicted. Mostly in the power system, S and V given to you. So easily you can find out the I and Z. Then you should know the formula between these two, okay? So how we can calculate the I? Simply you can using the Ohm's law, correct? Or you can using this formula, S equal VI conjugate. So we are ignoring the conjugate, so S equal the I equal S over V, as simple as this one. Then don't forget, if it is three phase, you need a square 3 by here, right? Then what about Z? The Z is coming in the way, V power of 2 over S. Don't forget here, no need to consider any square 3, okay? So this is the formula for Z. This one is the formula for I. Then for the base system, we must choose, as I mentioned, we must choose two of these as a base. So the other bases also can be find out using this formula. Assume we have S base, means selected, and V base. then the I base and the Z base can be calculated. In the per unit system, the per unit system also help you to covering the problem of the different sizing. Assume you went to the market and buy a transformer by the as a transformer value is 33 to 11 kV. Then the the power of the transformer is 40 megawatts, megavolt amp. And then the Z in per unit, the Z of the transformer given to you in per unit or percentage as a 0.2 per unit. Okay. Then in your power system you have another component which is a generator. That one generates in the 11 kV. So this one you can see it's still in range. The S for this one is 50 megavolt amp, and then the Z is equal 0.2 again, just assume, okay? So what is the problem by here? The problem by here is this Z per unit, using this S, and this Z per unit using this S, where the S are not aligned. However, the V can be the same. You can see, assume this is the generator in 11 kV. It's connected to this transformer, which is 11 kV to 33 kV. So for this problem, we have to make both per unit system, both per unit impedance of given components on the same reference, correct? Right now the reference is different. This is not the same as this. So what should we do? There is two technique. Technique one, which is a timey one, you have to return this per unit value as a nominal value, how possible? Okay, it is in this way. Z per unit, or anything in per unit, equal to real value Z real. What is the real value? Over Z base. Okay, so we know Z per unit and we know Z base. So we can return it in the real value as a ohm. Okay. Then again, based on the standard one we can choose one of these as a standard and return it back to the standard one. Or on the other way, we can using this technique, which Z per unit in the new standard or in the new basis is the Z per unit in the old, S base new over S base old, V base old. Don't forget, don't check. This is old, new. Be careful. And then here we have power of 2, correct? So on the power of 2. Uh, this is much more easier since we don't usually the voltage are in range. So otherwise I try to give you a different voltage level for you only to understanding. Another things I have to mention how we convert everything to per unit. For example, V per unit, the voltage in per unit coming as the real voltage of the system. So V real over V base. What's the meaning of the V real? Okay, sometimes we check the voltage of the power system